Welcome students. So what we are going to discuss, we are going to discuss lattice crystals, and especially we are going to introduce the concept of reciprocal lattice, right? So why the lattice are important? Because especially these crystals, because and what is the essential feature of it? They have a specific orientation and specific positions. So it could be at this position, it could be atoms or a molecules. So we are going to abstract it further, and there are various other crystals which we are not going to talk about, and we are focused on this segment especially because this is what we use in the semiconductor devices, right? So if you look into the semiconductor devices, this is the metal oxide semiconductor field effect transistor. It has all type of material. You have crystalline material in it, you have amorphous oxide, that is SiO2, and a polycrystalline silicon as a gate material. And we are going to focus on the crystalline part because the most important action, that is the flow of a carrier, happens in this region, right? So this is the sort of a most sort of a, significant part. The action is taking place here. So to define a crystal, we are going to define an abstract concept called lattice and basis. Lattice plus basis makes the crystal. So to go for the crystal, we are going to define an abstract called. So we are going to, crystal would be equal to lattice plus basis. We will see what does it individually mean. So so this is our approach. Let's see what is lattice. So these lattice, are often called Bravais lattice. So these was defined by this crystallographer Bravais, and the name is synonymously used, lattice and Bravais lattice. If I use lattice, think this I'm talking about Bravais lattice, right? So it is defined in a Bravais lattice. Every point has the same environment to each other point. So if this is the case, if every point has to have the same environment, then it has to be the infinite, because the finite system cannot have a same environment, right? And if this is true, right, that means the Bravais lattice can be constructed by translating a primitive vectors. So as we have seen in the class, we have established these two definitions were equivalent, and so we are just going to assume that we know these are equivalent, and a Bravais lattice is defined by three primitive vector a1, a2, a3 for 3D system, right? A1 and a2 for the 2D system, and a single vector for 1D system by an integer number, right? So note any vector r is a possible period of a Bravais lattice. So a Bravais lattice has this, any lattice points shall be described by this r vector, right? So this is the sort of a quintessential feature of the Bravais lattice, right? So whenever somebody tells you think about Bravais lattice, it should occur to your head there are three primitive lattice vectors, and that construct the Bravais lattice vector r, right? So any point, and you can take any point as an origin. So here is an example. All these lattice points can be covered by these two primitive lattice vectors a1 and a2. So m, n, and p, they are basically integers. They have to be integer. That's the essential. So to define a Bravais lattice, we need to know this primitive lattice vectors, and our job is done in a way, right? But all this symmetric looking structure, let's say this one, is not a Bravais lattice, right? Even this honeycomb structure, which looks like kind of symmetric, it's like have a nice shape, but it is still not a Bravais lattice, right? And one important point, this primitive lattice vector doesn't have to be unique. So there may exist a large number of choices to these primitive lattice vectors. So let's come to a simple cubic Bravais lattice, and it has these three primitive lattice vectors, and you can construct this cubic Bravais lattice out of it. And similarly, we have this BCC Bravais lattice, and these are the two possible choices of primitive lattice vectors, right? This is choice 1 and this is choice 2, but you look at the choice 2 is a more symmetric choice. This is x is negative, y and z are positive. In the A2, y is negative and x and z are positive, and similarly on A3, right? So sometimes this symmetric choices have distinct advantage when you are solving a problem, right? Similarly, if you come to the FCC, these are the three primitive lattice vectors. So if somebody gives me primitive lattice vector, I essentially know what is going to be the Bravais lattice, right? Okay. Now let's come to the unit cell. A unit cell is the sort of a simplest repeating unit which can kind of construct a whole lattice. So here I have written crystal, but it is essentially, it has to be lattice. Okay. And as the primitive lattice vectors were not unique, so the unit cell are also not unique, right? And now come to the primitive unit cell. So the primitive unit cell are the one which contain exactly one atom in a one cell, right? So this is not a primitive because it has two atoms, one fourth contribution from the corner and one inside, so it's not a primitive lattice cell. So the primitive unit cell are also not unique, but there is some primitive unit cell called Wigner-Seib primitive unit cell, which is unique, and you can construct it by taking a reference point of an atom, right? You take a reference point and join its all the neighbor. Note that you have to join its all the neighbor. It's not the nearest neighbor, you join all, and then you bisect the joining line, and whatever shape that you produce, that is called the Wigner-Seib primitive unit cell. So Wigner-Seib primitive unit cell is kind of unique, right? Okay. So this is the Wigner-Seib primitive unit cell for FCC and BCC. So primitive unit cell sometimes look horrible to look at. Let's say for BCC it's truncated octahedron, and for FCC it's rhombic dodecahedron, kind of complicated structures. But these are unique, so they are not used always as a reference. But in some cases, let's say to construct a band structure and all those things, we will come to back this very important concept of Wigner-Seib primitive unit cell, right? Okay. So let us say in 1D case, we want to talk about 1D, and this is the a simple 1D chain, and these are the various lattice points, and that is it basically, right? Now when we come to this 2D, in 2D we have maximum 5 type of Bravais lattice which are described here, and in 3D this was the major contribution by the Bravais, that all the systems if you have a 3D lattice, you can have maximum 14 type. All the systems on all the lattice point in the world shall be in one of these 14 Bravais lattice, right? So we are talking about this abstract concept called lattice, in which each point has the same environment. I'm not using the word atoms, it's point basically in the lattice, right? And based upon symmetry, there is another categorization where we have 7 lattice systems as per the symmetry, and in the 14 Bravais lattice, along with these 7 lattice systems, we have this simple cubic, volume centered, face centered, and base centered positioning of the lattice points, right? And we will be in this course, our central focus would be cubic, because most of the semiconductor that you are going to use are cubic. So it's a nice thing. And the cubic has this 3-fold axis of rotation. If you put a body diagonal, you can rotate the cube by 120 degree and get the same cube. So you are rotating it by 120, so you eventually say it's a sort of a 3-fold axis. So you can fold 360 by 3 times, you can fold it by 3 times, you get to the same position, but each fold give you exactly same position, right? Now coming to as I said, that crystal is basically lattice plus basis. Basis is something that we put at the lattice point. It could be even flower, just to make it more cartoonish. But we are going to put, instead of flowers, we are going to put atoms or even molecules or even a set of atoms. All is fine. So how do we, let us say this system, right? This is hexagonal system. This is not a Bravais lattice, because if you look at a point, it has a different environment. It has a two neighbor this way and one neighbor this way, whereas B point has two neighbor on its front. So A and B doesn't have a same sort of environment, but we can convert it back to a regular lattice or Bravais lattice. How? We just say, okay, A and B are combined as a one unit and they form the basis. You see, they form the basis, and this is the underlying Bravais lattice, and that is it basically, right? And this unit cell, this hexagonal structure is shared by the graphene. Graphene has this nice and hexagonal structure in the 2D. Okay, so the Bravais lattice can be converted into a non-Bravais lattice, can be converted into a Bravais lattice using the concept of a basis, right? Okay, but so this is like, but there exists some symmetric structure, let's say Penrose tiling, which cannot be converted into Bravais lattice even if you take some appropriate basis. So it's not always convertible, but most of the time convertible. Now we shall start with some concept called reciprocal lattice, or more generically called reciprocal space. What do we mean by reciprocal space? We'll come to this presentation, but let us go to the pen and paper approach to understand it. Okay. So all of you, I guess, are aware of this fact that any periodic signal, let's say in time, can be broken into the frequency. Let us say this is a square pulse, and its frequency is, its envelope function is a sinc function, that is sine x by x function, and these are the various frequency components, right? You have omega naught, minus omega naught, minus 2 omega naught, plus 2 omega naught, and something like that, and both are kind of equivalent description. So frequency is the reciprocal space of the time. You're changing the sort of a time axis to a frequency axis. And why do we analyze it? Because if you see here, in the time, the signal is ranging from minus infinity to plus infinity. But whereas in the frequency, it is going to be restrained into somewhat finite number of this omegas to a great extent in the most of the cases, right? So the frequency and time kind of are basically reciprocal pair. So T and omega are pairs, right? So this is the concept of a reciprocal pairs. So one thing, if somebody asks, how do you know what is omega? So you say, sir, we have done the Fourier analysis and we know that the basically omega naught is 2 pi by t. T is the time period of the signal, right? You see, this is the time period, and you put this, right? And what are the various? So our objective, is we want to first understand. Okay, so let's see why we are doing it. We have seen this crystalline system, which has basically made up of lattices, and when we deal with the crystalline system, so in the lattice points, we are going to put some atoms or molecules. So what will happen? The potential energy of these molecules will be periodic, right? You imagine in the 3D world, there will be 3D periodic functions of the potential energy. So we would like to have some similar approach if we can break these periodic functions of the potential energy into a Fourier component of it. Or in generic sense, we will say we break this into the in the reciprocal space, right? So if I want to construct a reciprocal space, what are the allowed sort of reciprocal space values. So that is I am interested. So first is like this 0, and then you have omega naught, then you have 2 omega naught, and so on, right? Similarly, you have here minus omega naught, 0, minus 2 omega naught, and minus 3 omega naught, and so on, and extending up to minus infinity to plus infinity, right? So let us say we have this time and we start to mark after each time some points. Let's say, right, I have this t, 2t, I have 3t, and so on, right? Similarly, I have minus t, minus 2t, and so on. So you see, if you have a periodic function, right, the time axis, and if you take these cross as some kind of a points, these are some points, special points, you see they also form a kind of a, this crosses forms a, in a sense, Bravais lattice, but they are forming in the time basically. Even if you go to the each point, you see exactly same environment, right? So if this is the Bravais lattice of the time, and so equivalently this is the reciprocal lattice point, and you should notice that here this in the reciprocal space is also Bravais lattice. And if you go to any point, you can kind of move by a distance and still get the time. Now, why to restrain ourselves to time? We could have similar thing happening in the real space also, right? So let's say instead of time, we have some real space function, let's say some x, right? And we can say, okay, so I have here 0, and instead of time, I have a naught, some a periodic 2a, 3a, minus a, minus 2a, and so on, right? Okay. So what would be its reciprocal version? I would say, okay, so I will have some reciprocal access to the space also in the similar manner, right? In a very analogous manner, I have some reciprocal space, and let me call it K, reciprocal axis, and it will also have some origin, and then you have b1, b, 2b, 3b, minus b, minus 2b kind of thing, right? Where b is 2 pi by a. Okay, so this is how you can always go back and forth. This is like I would call direct space, called reciprocal space. So we want to establish a formal manner in which we can construct a direct and a reciprocal space, basically, right? So to construct a direct space, it's pretty trivial. I just need what is the primitive lattice vector. I say, the primitive lattice vector A1 is here is, I would say, some A x cap, and any point, let us say any point in this x-axis can be reached by this Bravais lattice vector R, which is n time of A into x cap, where n is belongs to integer, or in shorthand I will write I. Okay. Similarly, how do I construct this? I can say, in this case it's trivial. I can say, okay, so my primitive lattice vector is called b1, that is b time of x cap. Okay, so you see the and any vector, any lattice point in the reciprocal space can be reached by let's say m time of b x cap. You see, okay, so this is nice. So I can reach any point. So this is called reciprocal lattice vector. So any point, so reciprocal lattice vector is any point you can, let's say I want to reach this point, right? So this is my reciprocal lattice vector, right? So something like this, you're getting it. Okay. So, and where m belongs to, again, integer. So you see the reciprocal space and the direct space are again a Fourier pair to each other. Okay. Now we want to have a formal way to go from direct space to reciprocal space and vice versa. One thing I can notice that direct space vector A1 dotted with the reciprocal space vector B1 has to be 2 pi. This was the condition which gave us frequency, right? We are just making it like a generic. Okay, good. And similarly, I can say r vector dot k vector has to be 2 pi by some integer, let us say mn p, where p belongs to some integer, right? So this is the condition, which tells you the how to construct the reciprocal space, because once we know the direct primitive lattice vector, you need to get some vector which gives you a dot product of 2 pi. So this is like, I would say, sufficient condition but not necessary condition, right? Okay, so that means if it is a sufficient condition, you can have, a large possible reciprocal primitive lattice vector to reach from a one direct lattice space to a reciprocal space. Okay, good. Okay, so now let's extend the same idea to the 3D. It's 3D version, right? So if you have a 3D, what I have in the direct space, I have A1, A2 and A3 reciprocal lattice, primitive reciprocal lattice vector, and R, which is, let me call M A1 and A2 P A3 vector, right? So this is my direct, instead of a space, I'm just direct lattice space. I'm kind of constrained to the lattice points only now. Okay, so let me construct the reciprocal lattice space. How do you construct reciprocal lattice space out of it? You say, okay, you have some B1 vector, B2 vector and B3 vectors, right? Primitive vector in the, such that A1 dot B1 gives you 2 pi, or let me write this condition in more generic manner, such that AI Bj gives you 2 pi delta ij. This is canonical delta ij. This is ij is 1 is equal to j 0 otherwise, right? So this is the condition. This is the condition to jump from direct to reciprocal and reciprocal to direct back. Okay, so can you make a good guess, let's say one of the guess which can satisfy this condition? Okay, so I can just write some nice guess if you can satisfy this condition, so so let me write one guess and we shall see this guess is indeed correct. Okay, so let's say I want to construct b1. What I can do, I can say 2 pi a2 cross a3 divided by a1 dot a2 cross a3. Now if you take a b1 dot a1, you will get 2 pi. So this is just one of the intelligent guess, and since this condition is a sufficient condition, you can have more than one choice, right? This is not this condition is not necessary. So similarly, you can write this one as in a cyclical manner, a3 cross a1 divided by a1 dot a2 cross a3, 2 pi a1 cross a2 a1 dot a2 cross a3. So you see, this one is the vector triple product, and it gives you the basically, this is vector triple product, gives you volume of unit cell formed by primitive unit vector in direct space. So we will give this direct DLS, direct lattice space, and sometime reciprocal lattice space. Okay. So this prescription allows us to go from one space to another. Then the R can be written like this. Then the K in the 3D can be written as M and P you have used. So let's say HLK, H time of B1, L time of B2, K time of B3, where H, L and K belongs to integer, and M, N and P also belongs to integers. So what is this, the idea behind this constructing a reciprocal lattice is constructing the sort of so-called, x-axis. Here we had this omega axis of the reciprocal space. So we wanted to know these special points where I will have the features. These are the special frequencies points, right, in the 1D. And when we have a 3D system, 3D lattice points, so what are those special points and how we can reach these special points. So this is the sort of it's a basically you take a direct lattice, its Fourier version is the reciprocal lattice, right? Okay. So now there is a formal definition to this reciprocal lattice vector, what we have seen in the formal definition. Okay, so but before we get into the formal definition, let's revise something that you might have studied earlier, that is called the plane wave. So we are going to take a detour and revise uniform plane wave. So uniform plane wave is described by e raised to the I kx minus omega t kind of thing, right? If I want to drop the time variation, so this is called, k is called wave vector, and this is called frequency. You see, in the uniform plane wave, let us say I have some a naught. This is my uniform plane wave, right? Which is okay. So in the uniform plane wave, we have basically a product in the exponents of the time and frequency and wave vector and x, right? So the time and frequency are basically this reciprocal pairs, right? We have seen it. Similarly, the k wave vector and x has to be reciprocal pair. Okay, so if we had a wave, uniform plane wave, so why it's called uniform plane wave? Because when you see this wave, let us say moving in the x direction, right? In the plane that are orthogonal to x, this wave has the same magnitude in each of the plane. You take any plane and you freeze the time, and then you see at various x is equal to x naught, x is equal to x naught dash, this across the whole plane the wave will have the same magnitude, right? So these wave planes are called wave fronts, right? That you might have seen at your in some electromagnetic course and things like that, right? So if I have a uniform plane wave moving in some arbitrary direction, right? Let us say this is moving in some arbitrary direction, then it is described by a naught e raised to the power I k vector dot r vector minus omega into t. Okay, so the direction of propagation of wave is given by the k vector. This r is not direction of propagation of wave, because this is like r comma t, right? This is a function. R is the sort of you're varying r, right? So the k defines the direction of a propagation of the wave, right? And I can drop the time component, I mean, you do this, let's say you want to analyze only the spatial part, how the wave is changing in the space, and we can always, it's in exponent, so we can always multiply it with the e raised to I minus omega t, get the time whenever it's necessary. So the uniform plane wave only having the spatial component can be given by e raised I k dot r. So now let's come to the formal definition of the reciprocal lattice, space. It is, let's see what is it, right? Let's consider R let's see R constitute a Bravais lattice, that is direct lattice, and there is a plane wave called e raised to I k dot r. Set of all the wave vector that yield a plane wave with the periodicity of a given Bravais lattice is known as its reciprocal lattice. So whatever we have done, this is equivalent if we change r by r plus, this is the Bravais lattice vector, and if the wave remain intact, then you say for special case, for the case for which this is true, you call that as a, these cases are called a reciprocal lattice vectors, right? So you see reciprocal lattice vector, as we've seen, it's like a Fourier version of it, and these can be defined in this way, right? So that means this e raised to I k dot r, if this is true, then this has to be 1, right? If you open it up, that means this is k dot r has to be 2 pi by n is some integer, and this is the precise condition that we derived earlier, right? This is some integer, right? 2 pi into r, right? So r into k has to be, so you see r into k, these are vectors, has to be 2 pi by n, right? So there are two equivalent way of looking at it, and both way are legitimate. One is described in my notes and one is given in the slides, right? How do I construct a reciprocal lattice space? I mean, same construction that we have discussed, right? You need these three primitive vector a1, 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 a2, and a3, and then you can have three primitive reciprocal lattice vector, and you can kind of see. So these are the various questions you can try at your home. This is simple. And then we are going to define something called first Brillouin zone. So we saw that there is something called Wigner side primitive unit cell, right? So you take a Wigner, so you constructed, let's say, a reciprocal lattice space. You construct a reciprocal lattice space, and in that reciprocal lattice space, you construct a Wigner site primitive unit cell. That is called the brilliant zone cell. So you may say, okay, so okay, a lot of things, but is it essential? Yeah, it's very important, and we will see why it is such a big deal. And it is important when you construct the reciprocal lattice space, right? It is also a Bravais lattice. In the reciprocal lattice space, each point you move it by each point has the same environment. So if you take a simple cubic, then these are the primitive lattice vectors. You can get A1, A2 and A3. These are the reciprocal lattice vectors. So you see, the bigger the A, if you have a bigger cube in the direct space, in the reciprocal space the cube will be smaller, right? So similar thing used to be true, right? If signal is spread more in the time, in the frequency, that is condensed more, right? So similarly, if you have a bigger cube, bigger reciprocal, bigger direct, bigger large distance between the lattice points in the direct space, in the reciprocal space the points will be more shrunk. Okay, so similarly you can see for FCC the reciprocal lattice is BCC. Let's say you take this A1, A2 and A3, and from the given procedure you can find B1, B2 and B3, and you will see these are indeed the BCC, right? And for BCC this is FCC. It has to be like that, right? Okay, so with this we will stop our discussion about the direct lattice space, Bravais lattice and reciprocal lattice, and in the next lecture we will discuss about lattice plane. So thank you very much.